Good morning, everyone. I'm excited to welcome you all today as we dive into an in-depth overview of P-block elements. Today's presentation is titled P-block elements, an in-depth overview. We'll be exploring their properties, types, and significance in chemistry. So stay with me as we uncover the fascinating world of these elements together. Let's get started. Let's now take a closer look at the anomalous properties of the first element in group 13, which is boron. We will start by understanding its general electronic configuration. Boron has a unique electronic setup that influences its chemical behavior significantly. Moving on, we'll explore its chemical reactivity, which is quite interesting given its position in the P-block elements. Speaking of which, it's important to see how boron fits within the broader context of the P-block elements and how that shapes its properties. We'll also review a summary of boron and its compounds to get a comprehensive picture of its chemistry. A specific compound to highlight is diborane B2H6, which showcases some of boron's unusual bonding and reactivity patterns. Additionally, we'll discuss the variation in properties among the group 13 elements, emphasizing boron's distinctive features. Finally, we'll consider boron's position within the P-block element framework and how that influences its properties and applications. All of these points tie together to give us a deeper understanding of why boron behaves the way it does, setting the stage for further exploration of its compounds and uses. Welcome to the introduction. On this slide, I want to emphasize the importance of setting the stage for the rest of our presentation. We'll start by outlining what we'll cover today, making sure everyone is on the same page. This is a crucial step because it helps clarify our main objectives and the key messages I hope you'll take away. Throughout this presentation, we'll explore how these concepts connect to the overall theme, which is about understanding and improving our processes. So, think of this introduction as a roadmap that guides you through the details we'll dive into later. By the end, I want you to feel confident about the core ideas and how they relate to our broader goals. It's interesting to note that nonmetals and metalloids are found exclusively in the P-block of the periodic table. As we move down a group, the nonmetallic character tends to decrease, meaning elements become more metallic. In fact, within each P-block group, the heaviest element tends to exhibit the most metallic behavior. There are 6 groups in the P-block, numbered from 13 to 18. When we look at the electronic configuration, the last electron in P-block elements enters the outermost p orbital. Since there are 3 p orbitals, they can hold up to 6 electrons in total. This concept helps us understand the electron capacity and the chemical behavior of these elements, connecting back to the overall theme of periodic trends and element properties. Let's take a closer look at the position of P-block elements. As you can see, these elements are located in groups 13 to 18 of the periodic table. Their position is quite significant because it influences their chemical properties and reactivity. P-block elements include a diverse range of elements like nitrogen, oxygen, and the noble gases. This positioning also means they have their outermost electrons in the p orbitals, which plays a crucial role in how they bond and interact with other elements. Understanding where these elements sit helps us grasp their behavior in various chemical reactions and their role in both nature and industry. So, recognizing their position is fundamental to understanding their overall characteristics and applications. Let's now turn our attention to the P-block elements. As you can see, this section covers Group 15 and Group 16 elements, which are quite fascinating due to their unique properties. These elements are characterized by having their outermost electrons in p orbitals, which influences their chemical behavior. In the P-block, you'll find some essential elements like nitrogen, phosphorus, oxygen, and sulfur. These elements play crucial roles in various biological and environmental processes. For example, nitrogen is vital for amino acids and DNA, while phosphorus is key for ATP and bones. Oxygen and sulfur, on the other hand, are integral to respiration and protein structure. One important point to remember is that these elements exhibit multiple oxidation states, which makes their chemistry quite diverse. Their ability to gain or lose electrons in different ways allows them to form a variety of compounds, from simple molecules to complex structures. Connecting this to the overall theme, understanding the P-block elements helps us appreciate their significance in both nature and industry. They are not just fundamental to chemistry, but also impact our daily lives in countless ways. So, as we proceed, keep in mind how these elements influence biological systems, environmental cycles, and technological applications. This group of elements shows a wide variation in properties. Boron is a typical nonmetal, meaning it shares characteristics with other nonmetals like poor conductivity and a tendency to form covalent compounds. Aluminum, on the other hand, is a metal, but interestingly, it exhibits many chemical similarities to boron, which highlights how some metals can behave differently from what we might expect. Then we have gallium, indium, and thallium, which are almost exclusively metallic in character, showing typical metal traits like high conductivity and malleability. This diversity in properties really underscores the complexity and richness of the P-block elements. It also emphasizes how, even within the same group, elements can vary widely, which is a key point as we explore the periodic table as a whole. Let's take a closer look at the general electronic configuration. This concept is fundamental because it explains how electrons are distributed around an atom's nucleus. Understanding this distribution helps us predict the atom's chemical behavior and reactivity. Each element has a specific configuration, which follows certain rules like the Aufbau principle, Hund's rule, and Pauli's exclusion principle. These rules guide how electrons fill the available orbitals, starting from the lowest energy levels. By mastering electronic configuration, we can better understand periodic trends, such as atomic size and ionization energy. This knowledge forms the backbone of our overall understanding of atomic structure and chemistry. Let's take a closer look at the general electronic configuration of elements in the P-block. As you can see, the configurations typically range from ns2np1 to ns2. This range defines 6 distinct families within the P-block, each with unique characteristics. Starting with the noble gases, they have the configuration ns2np6, which means their outermost energy level is fully filled, making them very stable and inert. Moving to the nitrogen family, they have ns2np3 configurations, giving them 5 electrons in the p orbital. Next, the halogen family has ns2np5 configurations, with 7 electrons in the p orbital, which explains their high reactivity and tendency to form salts. The oxygen family, with ns2np4 configurations, contains 6 electrons in the p orbital and includes elements like oxygen and sulfur. Then we have the carbon family, with ns2np2 configurations, featuring 4 electrons in the p orbital. This family is central to organic chemistry. The boron family, with ns2np1 configurations, includes elements with just 1 electron in the p orbital, such as boron and aluminum. An important trend to note is that nonmetallic character decreases as we go down each group. This means elements higher up tend to be more nonmetallic, and as we move down, they become more metallic. Overall, understanding these configurations helps us grasp the chemical behavior and reactivity of these elements across the P-block. Let's take a closer look at Group 13 elements. These elements are quite interesting because they sit at a unique point on the periodic table, right next to the boron group. They include elements like aluminum, gallium, indium, and thallium. One key point to remember is that these elements are often characterized by their metallic properties, but some, like boron, are metalloids. Aluminum, in particular, is very important commercially because it's lightweight, durable, and resistant to corrosion. Gallium is fascinating because it melts just above room temperature, so it can literally melt in your hand. Indium is used in touchscreens and LCDs, showing its importance in modern technology. Thallium, on the other hand, is more toxic and used in specialized applications. Overall, these elements demonstrate a mix of metallic and metalloid properties, and they have significant practical uses that connect to our broader discussion of element groups and their roles in industry and technology. Now, let's take a closer look at the electronic configuration of these elements in the boron family. The outer electronic configuration is ns2np1, which means they all have 2 electrons in the s orbital and 1 in the p orbital. This configuration plays a crucial role in their chemical behavior. If you observe carefully, boron and aluminum have a noble gas core, meaning their inner electrons match those of the previous noble gas, simplifying their electron structure. However, gallium and indium are a bit more complex because they include a noble gas core plus 10 d electrons, which are in the d orbital. And when we look at thallium, it has a noble gas core, but it also includes 14 f electrons, which are in the f orbital, along with 10 d electrons. This layered configuration explains some of the unique properties and reactivity we see in these elements. Understanding these electron configurations helps us grasp why these elements behave the way they do in chemical reactions, especially within the context of the periodic table and their relationships to other groups. Aluminum is actually the most abundant metal on Earth and ranks as the 3rd most common element in the Earth's crust. It makes up about 8.3% of the crust's mass, coming after oxygen, which is around 45.5%, and silicon at approximately 27.7%. The key minerals we find aluminum in are bauxite, which has the chemical formula Al2O32H2O, and cryolite, Na3Al F6. In India, aluminum can be found in the form of mica, with the formula Cal3C3O10. O2, especially in regions like Madhya Pradesh, Karnataka, Orissa, and Jammu. Now, when we look at other less common elements like gallium, indium, and thallium, they are much rarer in nature. Speaking of rarity, in India, borax is an important mineral that occurs in places like Puga Valley in Ladakh and Sampar Lake in Rajasthan. Boron itself is quite scarce in the Earth's crust, making up less than 0.0001% by mass. Interestingly, boron exists mainly in 2 isotopic forms, 10B, which accounts for about 19%, and 11B, making up around 81%. Boron is considered a fairly rare element, and it typically occurs in nature as compounds such as orthoboric acid, H3BO3, borax, NADB40710H2O, and kernite, NADB4074H2O. So, understanding the occurrence of these elements helps us appreciate their abundance, distribution, and the importance of minerals like bauxite and borax in different regions. Let's take a closer look at the variation in properties. As we explore different materials or components, you'll notice that their properties are not uniform. They can vary quite a bit. This variation can be due to factors like manufacturing processes, material composition, or environmental conditions. Understanding these differences is crucial because it impacts how materials perform in real-world applications. For example, a material that seems suitable in one scenario might behave differently under different conditions. Recognizing this variation helps us make better choices and design more reliable, efficient systems. Ultimately, appreciating the variability in properties ties back to our overall goal of optimizing performance and ensuring safety in engineering solutions. As we move down the group, each successive element gains an extra electron shell, which generally causes the atomic radius to increase. This is because additional shells mean the outermost electrons are farther from the nucleus, making the atom larger. However, there's an interesting deviation here. For instance, the atomic radius of gallium, which is about 135 picometers, is actually smaller than that of aluminum, which is around 143 picometers. This seems counterintuitive at first glance, but it happens because of variations in the inner core electron configuration. Essentially, the way electrons are arranged inside the atom can influence its size, sometimes overriding the expected trend. This highlights how electronic structure plays a crucial role in atomic properties, connecting back to the overall theme of how atomic structure influences behavior. Let's talk about ionization enthalpy, which interestingly shows some irregular trends. As we move down the group, you'll notice that ionization energy generally decreases from boron to aluminum. However, an exception occurs with gallium, which actually has a slightly higher ionization enthalpy than aluminum. This anomaly happens because of the poor shielding effect of the intervening d electrons in gallium. Essentially, those d electrons don't shield the nucleus as effectively, so it takes a bit more energy to remove an electron from gallium compared to aluminum. This highlights how electron shielding and subshell structures can influence ionization energies in unexpected ways. As we move down the group, we notice a trend in electronegativity that initially decreases from boron to aluminum. This means that as we go from B to Al, the atoms become less eager to attract electrons in a chemical bond. However, then there's an interesting slight increase in electronegativity from aluminum to gallium, and it continues to go up marginally through indium and thallium. This pattern might seem a bit counterintuitive at first, but it makes sense when we consider atomic size. As the atomic radius increases down the group, the outer electrons are farther from the nucleus, which reduces the nucleus's pull on those electrons, leading to lower electronegativity. But then, because of noticeable differences in atomic size, like the atomic radius slightly decreasing or stabilizing at certain points, the electronegativity bumps up a little again. Looking at the table, we see that boron has an atomic radius of 88 picometers and an electronegativity of 2. Aluminum's radius is larger at 143 picometers, with a lower electronegativity of 1.5. Gallium's radius slightly decreases to 135 picometers, and its electronegativity increases to 1.6. Indium and thallium continue this trend, with 167 and 170 picometers respectively, and their electronegativities are 1.7 and 1.8. So the key takeaway here is that while the overall trend down the group is decreasing electronegativity, the atomic size differences cause subtle variations, especially noticeable when comparing elements like aluminum and gallium. This interplay between atomic size and electronegativity is crucial in understanding their chemical behavior, which ties back into the broader theme of how atomic structure influences element properties. Let's talk about the inert pair effect. This phenomenon involves electrons remaining paired in the valence shell, which means they tend not to participate in bonding as much as we might expect. Essentially, it's the reluctance of the s electron in the valence shell to take part in chemical bonding. This happens because the shielding of these ns2 electrons by the d and f electrons is quite poor or ineffective. As a result, these electrons don't easily get involved in bonding interactions. An interesting aspect of the inert pair effect is that it increases as you move down a group in the periodic table. So, the lower elements in a group tend to exhibit lower oxidation states because their s electrons are less likely to participate in bonding. This phenomenon is quite important because it influences the chemical behavior of heavier elements and helps explain certain oxidation state patterns we observe across the periodic table. Understanding the inert pair effect really ties into the overall theme of how electron configurations influence element properties and reactivity. Let's take a closer look at the oxidation states of group 13 elements. Boron and aluminum typically show an oxidation state of +3 only. In contrast, gallium, indium, and thallium can exhibit both +1 and +3 oxidation states. As we move down the group, there's an interesting trend. Due to the inert pair effect, the tendency of these elements to show the +3 oxidation state decreases. Instead, they become more inclined to stabilize in the +1 oxidation state. This means that gallium is most stable in the +3 state, followed by indium, and thallium is the most stable in the +1 state. Understanding this trend is crucial because it ties into the overall chemistry of these elements, especially their reactivity and bonding behavior. It's a great example of how atomic structure influences chemical properties as we go down a group. Stability in AlCl3 is actually due to the formation of a dimer, which means two AlCl3 molecules combine to create a more stable structure. This is a common behavior in many molecules that have electron deficiency. Speaking of electron deficiency, let's look at boron trifluoride, or BF3. Boron in this molecule is trivalent, meaning it has 3 bonds, But if you count the electrons around the central boron atom, you'll see there are only 6. That's because boron doesn't have a full octet. It's missing 2 electrons. This incomplete octet makes Bf3 electron deficient, and as a result, it acts as a Lewis acid. Now, why is that important? Well, Lewis acids are substances that can accept a pair of electrons, and Bf3 is a classic example. Understanding the nature of these electron-deficient molecules helps us grasp how they interact with other compounds, which ties right into our overall theme of chemical reactivity. So, recognizing how molecules like AlCl3 and Bf3 stabilize themselves or behave as Lewis acids gives us a clearer picture of their role in chemical reactions. Let's talk about chemical reactivity now. This is a fundamental concept because it helps us understand how different substances interact with each other. Essentially, chemical reactivity refers to how likely a substance is to undergo a chemical change when it encounters other substances or conditions. Some elements or compounds are very reactive, meaning they readily participate in chemical reactions, while others are much less so. For example, alkali metals are highly reactive, especially with water, whereas noble gases are quite inert. Recognizing the factors that influence reactivity, such as electron configuration, bond strength, and environmental conditions, really helps us predict and explain chemical behavior. This ties into the overall theme of understanding matter at a deeper level, helping us control reactions in industrial processes, pharmaceuticals, and even in everyday life. So, grasping chemical reactivity is key to mastering chemistry's practical applications. Now, let's take a look at this example involving boron and oxygen. When amorphous boron is heated in air at around 1000 Kelvin, it reacts with oxygen to form boron oxide, B2O3. This highlights an important concept: the action of air, specifically oxygen, on elements like boron. Essentially, oxygen facilitates the oxidation process, transforming elemental boron into its oxide form. This reaction is a great illustration of how heating in an oxygen-rich environment drives chemical changes, which is a key part of understanding material behavior under different conditions. So, in this case, the oxygen in air plays a crucial role in converting boron into boron oxide when heated at high temperatures. Let's take a closer look at this example. 2B plus thrusol Ta forms Ta busol thra. This illustrates how boron reacts with halogens to produce trihalides. When boron encounters halogens like chlorine, it tends to form these stable compounds, which are called boron trihalides. The key point here is that the reaction involves boron combining with halogen molecules to create these specific compounds. This reaction showcases the reactivity of boron towards halogens, fitting into our overall theme of understanding how different elements interact chemically. It's a great example of how the reactivity of elements determines the compounds they form, especially in halogen chemistry. Let's talk about reactivity towards water. Gallium and indium are interesting because they are not attacked by pure, cold, or hot water, which means they are quite resistant in those conditions. Thallium, on the other hand, is slightly more reactive than gallium and tends to form an oxide layer on its surface when exposed to water. This oxide formation is a key point because it affects how thallium interacts with water over time. To put this into perspective, imagine how aluminum behaves. Aluminum can decompose boiling water and release hydrogen gas, which shows a higher reactivity compared to gallium or indium. For example, when aluminum reacts with water, it produces aluminum hydroxide and hydrogen gas, indicating its more active nature. So, in the context of our overall theme, understanding these differences in water reactivity helps us see how various metals behave in different environments, which is essential in applications like corrosion resistance and material selection. Let's take a closer look at the anomalous properties of the first element in group 13, which is boron. Now, unlike other elements, boron exhibits some unique and interesting behaviors. For example, despite being a metalloid, it has a very high melting point compared to other elements in its group. This is quite unusual, and it points to its strong covalent bonding and complex structure. Additionally, boron forms compounds that are quite different from typical metals or nonmetals, often involving intricate structures like boranes. These properties make boron stand out and are key to understanding its role in various applications, from electronics to materials science. So, recognizing these anomalies helps us appreciate how boron defies simple classification and behaves in fascinating ways. Boron is quite unique among the group 13 elements because it is a nonmetal, whereas the others are metals. This difference gives it some interesting properties, especially in terms of its allotropy, which means it can exist in different structural forms, unlike its metallic neighbors. Among all group 13 elements, boron stands out because it has the highest melting and boiling points, indicating strong covalent bonding within its structure. Speaking of bonding, boron only forms covalent compounds with a maximum covalence of 3, meaning it typically shares electrons with up to 3 other atoms. In contrast, the other elements in the group can form both ionic and covalent compounds, showcasing their more metallic nature. These features make boron quite an anomaly, highlighting how its nonmetallic character influences its physical and chemical behavior, which ties into our overall theme of understanding the diverse properties within this group. Crystalline boron is actually quite unreactive, which makes it interesting in terms of its chemical behavior. For example, when magnesium reacts with boron, it forms magnesium boride, Mg3b2, through this reaction. 3Mg plus 2b gives Mg3b2. This illustrates that boron can form stable compounds with active metals like magnesium. Now, moving on to oxides and hydroxides of boron. These are weakly acidic. That's an important point because it contrasts with other elements. For instance, aluminum's oxides and hydroxides are amphoteric, meaning they can act as both acids and bases. But for most other elements, including the rest of the group, their oxides and hydroxides tend to be quite basic. Also, boron hydride is quite stable, which is somewhat unique among hydrides. In comparison, hydrides of other elements are usually less stable. This stability of boron hydride again emphasizes boron's distinctive chemistry. Finally, only boron can combine with highly active metals like magnesium to form borides, highlighting its unique ability to create such compounds. This overall behavior of boron, its unreactivity in some forms yet ability to form stable compounds with active metals, fits into the broader theme of its versatile but distinctive chemistry. Now, let's take a closer look at this reaction. 2b plus 6Na-O reacts to form 2Na3Bo3 and releases 3 molecules of hydrogen gas. Essentially, what this shows is that boron can interact with alkali, like sodium hydroxide, to produce borates. During this process, hydrogen gas is evolved, which is a key indicator of the reaction taking place. This example highlights how boron dissolves with alkali, forming stable borate compounds. It's important to note that such reactions are fundamental in understanding how boron behaves in basic solutions. Overall, this interaction underscores boron's versatility and its ability to form various compounds when reacting with different substances, which ties into our broader theme of boron's chemical behavior. Diborane, with the chemical formula B2H6, is a fascinating compound that plays a significant role in the world of boron hydrides. It's a gaseous, highly reactive substance that contains 2 boron atoms and 6 hydrogen atoms. What makes diborane particularly interesting is its unique structure. It features these bridging hydrogen atoms that connect the boron atoms, leading to some unusual bonding characteristics. This structure gives diborane distinctive properties, such as its volatility and reactivity, which are important in various chemical processes. Understanding diborane helps us appreciate the complexity and versatility of boron hydrides as a whole, reinforcing the broader theme of how these compounds can be used in different applications, including synthesis and materials science. Diborane, which is also known as B2H6, is actually the simplest boron hydride out there. It's quite interesting because of its straightforward structure compared to other boron hydrides. To produce diborane, we start with boron trifluoride, or BF3, and react it with lithium aluminium hydride, or LiAlH4. This reaction typically takes place in a medium like diene-ethylene, which helps facilitate the process. The key point here is that diborane's preparation involves these specific reagents and conditions, highlighting how boron hydrides can be synthesized through reduction reactions. Understanding this process ties into the bigger picture of how boron compounds behave and how they can be manufactured for various applications. So, in essence, diborane's simplicity makes it an important reference point when studying boron hydrides overall. Let's take a closer look at some of the key properties of this substance. First, it's quite remarkable that it can catch fire spontaneously when exposed to atmospheric air. This means that it's highly reactive and requires careful handling to prevent accidents. Its boiling point is around 180 Kelvin, which is extremely cold, well below freezing, so it's definitely a cryogenic liquid or gas under normal conditions. Additionally, it's a colorless gas, which makes it hard to detect visually, and it's also highly toxic. This toxicity highlights the importance of proper safety measures when working with or around this substance. Understanding these properties helps us appreciate the challenges and risks involved in its storage and use. Throughout this presentation, we're emphasizing how critical it is to recognize these characteristics to ensure safe handling and to mitigate potential hazards. Let's wrap up with a quick summary of boron and its compounds. Boron is a fascinating element that plays a unique role in chemistry. It's known for forming a variety of compounds, each with its own interesting properties. These compounds are important in many industrial applications, from glass production to cleaning agents. What makes boron stand out is its versatility and the way it can form complex structures. Throughout this presentation, we've seen how boron's chemistry connects to broader themes like material science and environmental impact. Understanding boron and its compounds helps us appreciate the diversity and significance of elements in real-world applications. Boron, in its crystalline form, is quite unreactive, which makes it rather stable under normal conditions. However, when we look at amorphous boron, the story is a bit different. Under specific conditions, amorphous boron can actually react, which opens up interesting possibilities for its applications. This contrast between crystalline and amorphous forms highlights how the structure of an element can influence its reactivity. It's a good reminder of the importance of atomic arrangement in chemistry. Throughout this presentation, we've seen how the different forms and compounds of boron contribute to its unique behavior and usefulness in various fields. Let's take a moment to look at some of the key uses of p-block elements in industry. Indium, for example, is primarily used in coatings and alloys, which helps improve their durability and performance. Aluminum, on the other hand, is widely used in electrical devices and construction materials due to its lightweight nature and excellent conductivity. Moving on, gallium finds interesting applications in amplifiers, solar cells, and even satellites, showcasing its importance in advanced technology. Boron is another versatile element. It's valuable in producing glasses, ceramics, and plays a crucial role in agriculture by enriching soil. Lastly, thallium is utilized in photoelectric cells, but we should note that it is considered toxic, so handling it requires caution. These applications highlight how each element's unique properties make them essential across various industries, tying into the broader theme of how the structure and properties of p-block elements influence their practical uses.